Good morning, good afternoon, good evening. Welcome everyone to the new webinar from our phase 1 webinar series. So I see that lots of people coming in still. So we will start, I would say, in a couple of seconds. So yeah, our today's webinar is made together with Pheno-Inspect GmbH from Germany. Pheno-Inspect is developing dedicated image processing software for the breeding and agriculture sector. It automates the evaluation of the essential parameters of the phenotyping process. Artificial intelligence and algorithms provide the ability to learn with every new image and efficiently adapt to plants, problems, and local characteristics. Yeah, let me introduce you today's presenters. My name is Carsten Wieser. I'm part of the phase 1 sales team since more than 12 years and since quite some time acting as integrator sales manager. I'm based in Cologne in Germany. And from Pheno-Inspect in Germany, I welcome Dr. Philipp. He founded the company Pheno-Inspect in January 2020 to increase the technology level in digital phenotyping and plant breeding and agriculture, and make it available for every practitioner worldwide. Philipp holds a PhD in the field of machine learning, computer vision, and robotics. Welcome, Philipp.
Hi, thanks, Carsten.
So before we start the webinar presentation, I do a short introduction to phase 1 and our products. At the end of the webinar, we also have some time for question and answers. So if you from the audience have some question during the webinar, there's a little question chat box in the GoToWebinar app. And you can also, during the webinar, already type in questions if you have some. And at the end of the webinar, we will take care of these questions so that you get all the necessary answers. Yeah, let's start now with the corporate part of the presentation. So, and then afterwards, I will hand over to Philipp then. So phase 1 is a world leading provider of digital medium format imaging solutions founded in 1993 in Denmark. We provide ultra high resolution cameras and highly productive software solutions. We operate several sales and support centers for phase 1 across the globe. In Denver, Colorado, it is for the Americas region. In Cologne, in Germany, for the EMEA region and Australia. And in Hong Kong, we operate an office for Asia and South Pacific regions. Our company headquarters is based in Copenhagen, in Denmark, together with our main R&D center. Further R&D and production centers we operate in Israel and in Japan. In addition, we have more than 50 distribution partners, which offers a global network of sales and support centers, which makes us a fully customer-centric organization offering 24/7 support. Yeah, we really serve the world-leading brands with top image quality and productivity in various applications. Let me now give you a short overview about our phase 1 aerial products. Phase 1 has been supplying specialized cameras for a wide range of aerial photography applications since 2012. Those cameras are always made on the edge of technology by using the most modern sensors available on the market, delivering the best possible image quality. Over the years, we have continuously developed these products to meet the market requirements. Since 2017, phase 1 has also started to offer integrated systems for the market. These phase 1 aerial systems, or PAS systems, are turnkey solution for aerial survey flights. Today, we offer also, the PAS 150 Mark II, a medium format camera system with 150 megapixel resolution, the PAS 280 Mark II and the PAS 280 Mark II 4-band. It's a large format aerial camera system with 280 megapixel and more than 20,000 pixel cross-track resolution, followed by the PAS 880 and phase 1 large format and oblique camera system with 280 megapixel nadir view and 4 times 150 megapixel oblique view. These systems are dedicated for manned aviation. Then we also started recently also an integrated system for a drone payload. So we call it the P3 drone payload. And this is the latest addition to our portfolio and offers easier integration of phase 1 IXM cameras to DJI or Mavlink-based drones. Here you can see the phase one camera range today. The IXM camera with 50 or 100 megapixel, the IXM-RS camera with 100 or 150 megapixel, and the two large format cameras with 190 or 280 megapixel. The cameras of the IXM series can be easily integrated and used in a wide variety of aircrafts. Due to its size and weight, the IXM is the ideal camera for all unmanned drones or anywhere where size and weight matters. The cameras of the IXM-RS series, with their even higher resolution, are part of the phase one aerial systems, but also are built into a wide variety of aerial imaging systems made by many other integrators around the world. These cameras are also often part of airborne LiDAR systems and helicopter-based inspection systems. The IXM series cameras are often used in drones and inspection applications, such as inspection of bridges and roads, pipelines, railways, wind turbines, power lines, in agriculture and phenotyping application, where we get a deeper insight today, and as well as in mapping applications that required highest level of accuracy. The IXM-RS models are mostly used on larger areas in manned aircraft, also for mapping applications in agriculture and forestry, but also in environmental monitoring or for 3D city models and next to airborne LiDAR systems and also for inspection. That was already the part from my side. So I now will hand over the presentation from Philipp, and already curious to see his presentation. So here you go, Philipp.
Thanks, Carsten. Can you see my screen?
Yes, good.
All
Thanks.
right. Then, yeah, welcome everyone also from my side. I'm going to talk about the PhenoInspect GmbH in the next 30 to 40 minutes. And I will provide you with information how we squeeze out useful information using drone image data in the context of field phenotyping. Before I dive into the content, let me briefly sketch the roadmap of PhenoInspect's development. So all started in 2015 when I started my PhD at the University of Bonn. And I had the topic to develop robust and reliable plant classification systems for agricultural robots, such as UAV systems, but also for field robots for online applications. And during, let's say, 5 years, I developed the system and found people who have the same interest, built a competitive partner, people, and already customer network. And together with my today's colleagues, we are today 4.5 people, but arrows show up, so to say. We founded the company in 2020, in January. And basically, we had a very good first year and also looking forward in the second year in 2021. And I'm happy to say that we are now already serving our products and services around the globe. But enough from the company side, let's dive into the topic. So what is field phenotyping and why it is important, basically? And first of all, phenotyping means nothing more than measuring the visual appearance of the plants. And why you need it, consider yourself for a moment as a breeder. And your goal is, for instance, to breed a new variety, which has certain properties, which are better than the varieties, other varieties or varieties which are already on the market. For instance, let's take the sugar beet for an example, but this holds for any other crop as well. You want to breed a variety which is more stress tolerant, which is more competitive against weeds, which is more yield effective, things like that. And what you need to do for developing this variety is you need to observe on a continuous basis the performance of the plants of your different varieties you have in your genetic pool, so the genotypes you have in your database, so to say, in the field, and compare these performance with each other and across different locations, across time, in order to find the most promising candidates to cross them again. And in the next generation, you hopefully have a variety which has already the new property inside. And this is a process which goes typically over years. So 8 to 12 years is the typical breeding cycle. And in the end of this, you want to bring it to the market, and then you have to register this, and then the variety has to be tested. So just having this breeding cycle in mind, you can imagine that there is a lot of phenotyping, so measuring work in the field. And here you see in the background a typical breeding field. It's a size of 4, but also larger sizes are possible, 4 to 10 hectare, let's say. Here it's 4 hectare. You have around 3,000 to 4,000 plots. In the plot, you typically plant a certain variety. You repeat this over the field, make a randomization of this. You perform different applications in this field, and you are interested in the performance of the plant within every plot you see here. So what is typically measured? So a common measure is counting the plants. You want to know at the emergence what's the number of plants which made it, and even or also for before harvest, you want to know how many plants contribute to your yield result, for instance. So counting is really one of the common things which are done. Then morphological assessments. So what's the shape of the plant? What's the length of the plants? Are there certain shape properties which are basically aligned with your breeding goal? Disease and stress scoring. So is the plant more or less affected by a certain disease or by a certain stress under certain environmental conditions? Homogeneity monitoring. So you are interested in knowing how homogeneous is the growth of your plants or of your experiments. Agronomic events. When starts a certain variety to flower, or when certain plant origins, fruits are builded. If you think about it, you can turn it down to one sentence. So you are interested to find specific objects in the field, and this on a regular basis, more times during a season, and on a large scale, if you consider the field in the back. So you can imagine that this is a kind of a laborious task, and it's very cost intensive, because you not only have to send random people into the field which can assess this, you have to send experts into the field which know what a disease looks like and what certain properties are. And you have to send many people in the field in order to measure the entire fields more times a season on different locations. So there is the question of objectivity. So basically, if you have more people measuring the same thing, person A says, it's a 4, person B says it's a 3, you get kind of a blurry result in the very end, which raises the question, can we do better here? And this is exactly the thing where PhenoInspect kicks in. So what we are doing is basically we combine or use state-of-the-art drone technology, basically, as imaging sensors. So here you see an M600 equipped with a phase 1 100 megapixel RGB sensor. And we develop the artificial intelligence, so the digital expert, what we call it, in the back end, and analyze the image data which is captured of the field and extract the traits of interest fully autonomously and on a large scale. And just as a comparison, so this drone flies in around 30 minutes flight time across the entire field, giving us an entire image of a ground resolution of 2 to 3 millimeters. And with this kind of details, you can do a lot of interesting stuff, and this I will show you in the next slides. First of all, that you understand what is the result. On the right side, you see this plot structure mapped, overlaid onto this image. So there is the entire automosaic, so a registered image of the hundreds of single images that were acquired during the flight. And then you detect or create the plots, overlay them on the image, and then for any plot you see here, you extract the traits, and then this, what you see here in the grayscale bar, is basically an overlay of a certain trait. Let's say it's the plant count or even a disease score for each plot. And this is basically the result the breeder or the grower is interested in. So let's start with the first topic, emergent scouting. So with emergent scouting, I refer to everything which happens in the youth stage of the plants. So basically, after they emerge out of the ground until they reach a certain growth stage, this might be different for different types of crops, but it's early in the season. And this is important for variety testing. It's important for variety selection, so to say. And it's very laborious. Just consider you have to count all the plants which are below on the ground and which are very small and on a large field. So here's the first example I brought you for our sugar beet emergence counting. So you see that we first detect the single plants. So the green guys here are the sugar beets and the red guys are the wheats. And you also see that this classification is well done under different conditions, sunny, straw in the background, shadow, cloudy, whatever. So this is really something which our engine can solve very robust and reliably. And what you see else is this red lines in the crop rows. These are the gaps where we also estimate the number of plants which are missing there. We analyze the size of the different plants, the variation of the size in the plot. We estimate the number of weeds. We can also go into multi-weed species detection if desired. So here's another example. As we are crop agnostic, we have digital expert for a bunch of crops already, and this is growing on a weekly or monthly basis. And here is an example in corn. So this is a bit more challenging because plants start overlapping even earlier in the season, but still our engine is able to properly identify the single plant. And this is always the basis for any other higher level traits which are derived from that. For instance, here is the plant count then, plant count per row in this case. So red means a lot of plants, blue means less plants, and the other traits you can easily visualize, and you get with one view directly the overview of your entire location or even across locations if you like. Another example here is in soybean. It's the same story in the end, but I wanted to show you that, to show the variety of crops types we are dealing with. This is a field somewhere in South America where we look a bit more into the variation within a plot. So, but even here it's the same, that first the single plants are detected, then the weeds are detected, the gaps are detected, crop rows are detected, further traits are developed based on this low-level traits report. All right, so now emergence is in the very beginning, but what happens later in the season? Later in the season, the plants start to grow more and more, they get of bigger size, they overlap each other. At some point in time, you have the complete closure of the canopy. Still, plant count is always an important trait because now you want to know how many plants are still there, how many survived, and how many contribute to your yield in order to estimate the yield per plant, which is an important parameter later. Stress and disease become more and more important as later in the season it becomes, so to say, because then diseases start to spread, and then you have the chance to observe which variety is more tolerant, which one is less. And I will show a bit more details on this later in this talk. Another nice application which is very beneficial for our users is ear counting, or more generally fruit counting. So on the left side you see analysis of detected ears or heads, however you want to call it, in rye, barley, wheat, but other crops are possible here. So it's really a matter of the data and if we have a digital expert already ready or if we have to develop it. And this is our strength. We are very good in fastly developing new digital expert for whatever problem you have. On the right side, you see a Phantom 4 flying over the field. And on the left side, this is the actual data from the Phantom, where you basically, or where I say, okay, this is the most you can get out of the Phantom. So this is a ground resolution of around 1.5 to 2 millimeters, and 2 millimeters and below, there begins the sweet spot for high accuracy ear counting applications. And this is, of course, possible with the Phantom, but not at a very high throughput, as the sensor is very small, and you have to take, if you have to cover large areas, then you have to spend a lot of time in the field in order to measure this. But just from the analytics side, this is what you can do. And the typical approach today is that people have a frame, which is a square meter or even a quarter of a square meter, and then they lie the frame on the canopy, count the ears in this frame, and then extrapolate the result to the entire plot, which is highly dangerous because there is an assumption in the end, in the back end, which says, okay, there's a uniform distribution. And this is the thing where we say that if you count with drones the entire plot, even if you are not perfect, so 100% of the years, nobody will achieve this, but 90 plus plus is possible depending on the data quality, is still better than you would when you would do manual counting in the end. And it's time saving, and you can do it on a very large scale in the end. All right, if you turn this ear counting example into the open field domain. So let's leave the phenotyping domain for a second. In the open field, you can do the same thing. So this data is acquired with the phase one. It's a ground resolution of around 6 millimeters. And you can do enhanced application maps, or you can enhance your application maps with this. Why is this important? So if you are able to detect the ears in a certain region of the field, and you do it for the entire field, let's say tens or hundreds of hectare large field, you can spot even with single images, or you can fly over the entire field, depending on the size, of course. But with the phase one and 6 millimeters, you can cover a huge amount of area in a short amount of time. And then you can detect the ears in this case, and then you can count them and compare them against other regions in the field, and use this as further input for your application map, for instance, for fertilization. So of course, the recall suffers from the from the lower GSD. Recall means how many actual ears in the field I really detect. But this doesn't matter that much for this application, because you have a kind of a high precision. And this high precision means if I detect the ear, it's an ear. And this means you can relatively measure with a really good accuracy, because if you have a high precision, you can measure at 10 places in the field, compare, and you know, okay, there is less, there is more, and so forth. So in this, you can turn into an application map, which can look like this example here, for instance. So you have this colored boxes, where each box maybe sends another command to your machine. Please put more fertilizer here, or put more herbicide here and there. You can do different things here. So, and in this case, it's an example for a weed control application map. So the blue areas here are referring to places where everything looks fine. So you have no weeds, and you have a homogeneous distribution of your plants. So this is a corn example. So with around 1 centimeter ground resolution, we are able to count all the plants on the ground and also detect the weeds. And if we jump into this red box here, we see the red guys here. These are weeds which are growing in the crop row of the corn. So, and basically this is something which is possible now with this technology to find also the weeds within the row. Because if you think about it, 3-5 years earlier, the typical approach was, okay, I identify the green stuff, I maybe estimate the crop row, and then I assume that everything between the crop rows is wheat, but this doesn't work in this case, for instance. And with more advanced image analytics, you can gain more or better information and do a better job later in your actual application in the field. Coming back to phenotyping, what I think is the premier class when it comes to high quality data requirements, high quality analytics requirements. Here on the left side, you see an example. If you measure with the phase one, roughly flying at 21 meters, so with a millimeter or even a bit below, ground resolution over your wheat field. And on the right side, you see the classification result, which is possible with this kind of quality. So if you really want to make no compromise, you need high quality data and high quality analytics, and then you obtain the best results. And I think what you see on the right is there is not much space to improvement. So of course there are some ears which are may not seen because they are behind the leaves or so, but this no vision technology can serve. But I just want to stress here that if accuracy is the major requirement, then high quality data is key and high quality analytics is key. Let's switch the topic a bit to weed mapping. Weed mapping is also important in phenotyping applications, of course. So knowing what kind of weeds and how many of them are there. It's important for weed control, obviously. I showed the application map before, and it's definitely also important for agricultural research. So basically, a lot of research is done in the field of how can I do a better weed control, for instance, evaluating different new mechanical tools, different new robots, maybe also new chemicals, or other stuff which you want to bring into the field in order to say, okay, can I control my weed more efficiently? And for this, the typical approach is similar to the weed ear counting case I said before, is that the researcher typically defines a small window in the field and then measures very accurately the number of weeds, the number of plants, and the distribution of different weed species in this window, applies the application, and later the success of the experiments is derived from a kind of small sample. With the technology plus high resolution RGB data, it's possible to measure the entire field and measure based on the entire application area the success of the performance. So for instance, if you have a robot driving over the field and the task is doing mechanical weed control, you can measure the entire 1 hectare or even more, how many weeds he killed, how many grasses he get, and things like that. And here's an example I brought in a rapeseed field, which was measured with the phase 1 camera. So it's a 5 hectare big field. So measuring time was around 25 minutes. So it was 1 battery of the M600 in the end. It's under good conditions, I have to say. And the goal is to identify the rapeseed, which you see here in green, the dicot weeds in red, and the grass weeds in blue. And since we did it for the entire field, now the user is able to define much bigger application windows and evaluate the performance of the application or the different experimental questions based on a much larger sample size. And also in these conditions, you see in the, I think one of the last images, we are still able to count the rapeseed plants and also the weed plants. I don't have an image here, but also under these conditions with high weed pressure, able to count properly the plants. Here you see the image, which is also an important measure during this process. All right, so let's switch the topic again and let's talk about disease scoring. Disease scoring is a very important task in phenotyping, breeding, growing. Whenever it comes to agricultural applications and plants are involved, disease is always a big topic. And I just want to bring here some examples what we are serving already in sugar beet. Here we have 2 prominent diseases, which is what you see here is powdery mildew. It's this white film on the leaves, and on the right side you see CLS, psychospore leaf spot disease, which is small brownish circles at the size of 1 to 3 millimeters, and at higher infestation levels, these circles merge into each other and end up in this kind of brownish regions here in the field. Both diseases are very important diseases. They are yield effective, and therefore breeders want to know how good are their, or how tolerant are their varieties against these diseases, for instance, is one of the questions behind it. And by the way, the left image is done by a drone. So it's really a 1 millimeter shot, like comparable resolution like we saw before in the ear counting case, the very last one with the phase 1. And you really can say, okay, it's like the breeder's eye in the field. So basically you can do the phenotyping based on the photos if you like. All right, so let's start with the more easier example in terms of the computer vision with powdery mildew. Here are 2 plots. The top one is affected, the bottom one is tolerant. And you see here, this data is also acquired with the phase 1 at the ground resolution of around 3 millimeters. It was a very large field, we'll see this later. And the quality at 3 millimeters is still sufficient in order to really see the details, to see the symptoms of certain diseases. This is the result you see derived by our software. So red means there is a lot of infestation, blue means there is not much. And here you see in blue and green the pixels which are detected as affected, and the green ones are the healthy ones, and no color refers to soil pixels or shadow, let's say. So just as a comparison, this is how a healthy plot looks like. Of course, there are some neighboring effects, but this is covered by us as we only evaluate the center part. And it really becomes interesting when we now see, when we zoom out, that this result is done with one flight over the entire area of around 5 hectares in this case, so 4,000 and more plots, and you get the infestation map of powdery mildew for the entire location. And this is something where we are really in the sweet spot of combining high resolution imagery along with enhanced vision technology to make a real high throughput product here, which serves as a useful tool for growers and breeders. All right, another example, also mildew, is here we measured another location, but with even higher accuracy. So this is the data set where the screenshot or this picture was cropped out before I referred to. And here you see much more details in the end. And what I want to say is that the detection works as in the previous case. But if we zoom into a place where no mildew is detected and we look at the image, at the first glance you would see, okay, there is maybe mildew, and you can imagine that under a lower resolution it's hard to distinguish this. But with the higher resolution and the classification, which is able to deal with certain or with different conditions, sunny conditions and cloudy, overcast, different viewing angles, all these things, you can reliably and robustly perform the detection. And here's another big benefit, because the drone pilots which are listening now will know about it. There is always a recommended time when you should fly. Best around noon, plus minus 2 hours, and so on. Then you get the best images, the less effects, and so on. I say if you use high quality imaging sensors and you use our technology, you can basically fly from the sun from morning to evening, because this is really a data set which was captured under the worst conditions. It was close to sunset. The sun angle was really low, and typically if you look into the phantom images and so on, then you run into trouble because things will become indistinguishable to some degree. Therefore, I say, okay, the higher resolution is definitely also a point that you can achieve higher throughput if you consider you are a pilot and you want to measure 5 or more fields a day. All right. Here's another example in sugar beet. So here is the problem, the yellow virus. In Germany, it's called Vergilbung, the symptom. So this is this yellowish color on the leaves. And the goal is to detect it and to quantify it, to quantify the distribution of it. And you see the blue pixels here is the detection accuracy, or is the detection result for the yellow virus symptoms, or symptoms induced by the yellow virus. And the pink pixels are other stress symptoms which are not mappable to any reason, let's say. And in this case, we did it on single images. So you have your drone, you fly on a large area, you have to fly a large area, then you subsample the entire area with a scouting approach, let's say. So the drone flies, goes down to 3 meters, makes a picture, flies to the next waypoint, goes down, makes a picture, and so forth. And with this, you can cover a large amount of area. When it, for instance, is the question in a typical open field application. And you can then get the information about the distribution of your stress for each image, and then you can also, if desired, interpolate the stuff in your field boundaries if you want to do it. Or you can also select the subsample size or the sample distribution based on your throughput needs. All right. Last but not least, I want to talk a bit about the CLS, so psychospore leaf spot. And here we have the specific challenge that the symptoms to identify this specific disease are very small. So these are these small circles on the leaves, which are at the size of 1 to 3 millimeters. And later, of course, they merge into each other. They get brownish. You can measure from above, even with lower resolution, that, of course, it looks not healthy, but you're never sure if basically another stress is the reason for that. Of course, you have an idea about, or the breeder, the field expert, the guy who manages the field, has the idea about what stress is appears in the field at the current moment. But if you really want to detect directly the symptoms, you can use very high resolution imagery again, and then go directly for identifying the leaf spots and the merged regions here. So here on the right side, you see this green-blue dots. These are the detected CLS spots. And the pink is, again, these general stress symptoms where we are not sure about. All right, and this turns then into a psychospore pressure map, so to say. Here in red is plots or patches in plots with high psychospore pressure, and the bluish plots are the ones with less infestation. And basically, you see this pattern that the first, second, seventh, and eighth repetition is basically more affected, and this is expected as these are the repetitions where no fungicide application was performed. And this is first indicator for that, but let's dive into the details. Here you see a close-up of one of those patches, and you can really see the single leaf spots, and we have a digital expert for that, which explicitly identifies them, counts them, and combines this measure with the general stress symptoms we see in the image. And from this, we derive basically the psychospore pressure in the end. And we did an experiment, or several experiments also with breeders, which manually scored as usual. And we see already a very good correlation with their results. So around 95% of the deviations lie within scoring of ±1. For those who are not familiar with this ranking, typically you score from 1 to 9. So 1 means there is nothing, and 9 means there is a high infestation. And from the user side, or from the breeder side, from the plant expert side, there is also the statement that they typically say, okay, our measurements are lie in the accuracy of ±1, roughly. Depends on the experience and on a bunch of circumstances, so to say. So this really shows already that we are on the right track. Of course, there is space for improvement, and we will improve this. So we are currently coordinating a research grant together with the Federal Office of Varieties, Bundessortenamt in Germany, and the Institute for Sugar Beet Research and the University of Bonn, where we exactly look also into these things and pushing the boundaries of what is possible with this technology further. All right, we also looked into multispectral data. So here's the Altum sensor from MicaSense. Generally, we can say multispectral comes at the cost of having a lower GSD, lower spatial resolution, but having a higher quality color measurements, supposedly. And if you look at this patch on the left side, you see the RGB image, which was taken, I guess, with a Phantom 4 in this case, flying kind of low with 2 millimeters to 3 millimeters ground resolution. And on the right side, we really flew very, very low with the Altum to get the most out of it, but nothing more than 6 millimeters ground resolution is possible. And you can imagine that this doesn't scale to a lot, to a bigger area you want to cover. And generally, we see in most things we are doing, so most analytics we are doing, that there is not really the big gain in using a multispectral data. So you don't see the hidden features, is our experience at least. There are different opinions out there, but in the end, with high resolution RGB, you can detect most of the stuff as well. However, we also are able or capable of detecting or analyzing multispectral data sets. And here in this case, this is the mean NDVI we show here for these different patches. By the way, I have to say fairly that these images are not calibrated, so the values doesn't mean so much, but just to show that from the processing capabilities, this is definitely possible. And here we trained a classifier, and this is also nice. We don't rely on calibrated spectral bands. It's enough for us to have basically the data, and our digital expert can deal with both in order to find the right target if you have it in your training data in the end. And also what is possible is to compute all indexes you like, basically, and also including plant height measures. And for the plant height, I have a small other video I want to show here in hemp or cannabis, where the goal is to estimate the height variation. So what we do is our typical detection pipeline. We know then the cannabis pixels, the soil pixels, weed pixels. And what you see here is the point cloud derived from the photogrammetric model. And all the green points are basically pixels with a 3D coordinate which belong to the cannabis pixels. And the other ones are the soils. And then we estimate the ground plane basically, and then can use the points in order to estimate the distribution, mean, median, maximum, minimum height of the canopy, and also the variations, so standard deviations or other measures of the distribution. Let's switch to the last topic. Of course, we have also a web interface in order to serve our visual results worldwide, to allow you to upload measurement data, to manage kind of your projects. You can upload your data to our server, and then most of the stuff is done automatically afterwards. Here is what you get after you define your task and upload the data. You basically obtain a message that your data is now ready for inspection or is ready for being downloaded. And here in this case, it's a herbicide trial where the goal was to identify different weed species and to verify the success of the application. And basically, here you can just see that you can go through the data, you can look at it, you can zoom in, zoom out, you can put the classification on, you can look at the RGB image. You can also visualize the research plots, and you can visualize the numbers which are somewhere stored in the database in a visual manner, and get kind of a fast overview about the experiment. And of course, this is now showing a semantic segmentation. You can basically visualize almost everything here, which I showed before in the other examples. It's just a matter of what you export to the web interface and whatnot. All right. If you want to do your research or integrate the research plot yourself, you can also use the plot creation tool. It's a matter of some minutes and some training to get the plots done. And you can also rename them according to your plan and to your field plan and so on. You can also import and send us shape files if they are there, or you can also say that we should do this. It's not a problem. That also the full service can be handled from our side. In this case, just wanted to show you that it's really not a problem to get the plots into the image once the automosaic is computed. All right, another feature is basically that if we don't conserve any digital expert for you now, you can easily provide us some target training data. So you draw in the plants you want to detect, and or you can also provide multiple classes. You can draw on the fruits, you can draw whatever object you like and send it to us. We train the algorithm for you using our engine, and we provide you with the results you desire and so on. So of course, it's not just based on your training data. We have a huge training database in the back end and some intelligent mechanisms to put together the data you need in order to get the right expert for your dedicated task. But this is one of the opportunities you have if you're using our web engine in the end. Okay, and afterwards you can see the results based on your input. You can visually inspect it, and if you are happy with this, it's fine. If you are not, you can also provide further training data. You have access to the predictions, can improve them in order to create a better model for your specific task. And this is all possible just by using the web browser. And yeah, with this, I'm done with all the content. I think we can go to the question and answer sessions. I hope I could give you a rough overview about what we are doing and what are our goals and what is our capabilities in terms of data analytics. Thanks a lot.
Okay, thank you, Philipp, very, very much. It was very, good insights you show to your solution, what can be done with high resolution images and your software products for field phenotyping and for breeders and growers in the agricultural sector. So very, very much thank you for that. We have now some time to do some question and answers. So I just switch the presentation here, just a second. So, okay, good. So we have my colleague Dejan Dragic in the line, and he was also listening to the webinar and also collected the questions which come in. Dejan, did you have received some question for myself and for Philipp?
Yes, Carsten, thank you for introducing me. Also, thanks once again to both of you for hosting such an interesting presentation. And we have collected quite a lot of questions, actually. So in case we don't manage to answer to all these questions to the audience, please be aware that we have your email addresses and we will be able to reach you out in person, and we will answer all the questions that are left unanswered here. So let's start with a question maybe that one of the attendees asked. Which sensor you used for counting years in the wheat? Philipp, this is probably for you.
Okay, thanks for the question. So basically, the answer is any RGB camera is wrong. So you should use a good RGB camera. So of course, I can just recommend using the phase 1 100 megapixel camera. There you have no compromise. And if you have a big field, let's say you have 4 hectare of research trials and you want to count every single ear on the field, then it's recommended to use image sensors which provide you with a high resolution and a high quality, so to say. But you can also use the Phantom 4, to be fair. You have to fly lower. You have to make sure that your ground resolution is in the range of 2 millimeters, around 2 millimeters or below, in order to get 90 plus accuracy. So if you are fine with a bit less accuracy, you can also go to 3 to 4 millimeters. We also have tested this one, and the results correlate well as well with the manual counting, even with this resolution. But there are effects and influences which make it really hard to do this reliably. So if you really want to be sure that the result will be good, high resolution, high quality.
Thank you a lot, Philipp. Yeah, in addition to this one, I can also ask another question. So how much are shadows actually affecting the ear count?
Goes also to me, right?
Yes, that's right.
Okay, yeah, okay. So basically, the question is, again, a camera sensor, again, a sensor question. Because shadows are not a problem for our analytics pipeline as long as the value is not 0. So it should saturate to 0 or to 255 or to the maximum value to bring the other extreme also on the table. Then you don't have information, then you can't do something rather than guessing. And there is all, again is a sensor question. If you have a good sensor, you are able to see also things in the shadows better. If you have a cheap sensor, shadows become 0 very, very soonish. So this is the question. But from the analytics point of view, we can deal with shadows, we can deal with partial occlusions, we can deal with different weather conditions, with different colors of the crop, whatever conditions are in the actual or what appear in real life.
I can add some information to that from the sensor side. We're using from phase 1. So we're using the modern CMOS sensor with backside illuminated pixels from Sony, where especially the dynamic range is very big. That means if you have very bright areas in the image and very dark areas in the image, you always have I would say a lot information is collected between them. So it means if you have very dark shadows, very bright areas, you can in post-processing lift them up or bring them down to have a good automosaic image in the end to enable good analysis on the software part. So the chance that there is 0 information in the black, for instance, is very low because of the very high dynamic range of the sensor.
Thank you both. Yeah, one question now for the Carsten. On which drone can people use actually phase 1 cameras?
So yes, that's today a wide range of drones we support, and also our drone partners. So just to give you an idea, we just recently launched a P3 kit, which even more opens to different drone platforms. So we have a P3 kit ready for the DJI M300. We have an integration for the DJI M600, and we have lots of customers and partners which are building drones on Pixhawk based platforms with Mavlink protocol, and this is an interface or interfacing language we can use, and our camera knows to combine the camera into the drone and to communicate with the camera from the ground station. So it means you have full control about the imagery during the flight. You see the results, you get some feedback. You can change shutter speed, aperture, and so on. And there's a wide variety of drone partners. We can watch our website. There's a kind of list where you see which partners already integrate that. But if there's any drone you use today in the audience, just drop us a mail and we will help you to guide you in the right direction. Yeah.
Thank you a lot, Carsten. Now I think this one goes to Philipp again. Can you tell us more about the best heights or altitudes to fly phase 1 cameras for digital phenotyping?
Yeah, so in the end, your altitude you should fly is always a function of the sensor you're using and the analytics you want to do. Let's take the ear counting example. I said 2 millimeters or below. So if you want to really go sure and make 1.5 millimeters, then depending on the optic you have on the sensor, for instance, I can just talk about the 80 millimeters focal length optic because this we are using. Then you fly around around 30 meters altitude, and this is enough then for having this. So the thing is really not so. It's not the height. What should be the question? It should always be the question what GSD you are requiring for having a certain range or certain security for a desired accuracy. And this depends on the task. So it's easier to so for ear counting you need a higher GSD rather than for plant counting in general. And if you count sugar beets, for instance, it's fine to have 5 millimeters or more, depending on the growth stage, of course. But this is highly dependent on the application. But we can support with this. So if there are any questions regarding how should I fly, so we support our customers regularly in doing their own flights.
So I can also add some information here. So as Philipp said, the GSD is I would say what dictates the flying altitude. But a high resolution camera helps here to either fly high, so above the field, but in addition also still covering a large area per image. So to get you an example, so if you take a 20 megapixel camera, you need to fly for 1 millimeter GSD around 3 to 5 meters altitude, so very low and only cover a very small footprint. If you do the same with the 100 megapixel for phase 1, you already at 1 millimeter fly 21 meters altitude with the 80 millimeter lens, and then covering a much bigger area, which is nearly 5-6 times the size of the 20 megapixel image.
Thank you both. One additional question to Philipp. Is there a plan or possibility to count trees also with PhenoInspect and to determine tree species?
So the plan comes with the request that we should do it. So let's say we did it already on a smaller scale, let's say. So this is a tree school, Baumschule is it called in Germany. So where the tree grower or tree breeder needs to count the number of trees and also to distinguish the varieties of trees. And it's also a licensing question because the breeder allows the growers to grow, let's say, 1,000 of a certain variety on this field, and then they have to control it somehow. Therefore, yes, it's an actual thing, and yes, we can do it. If you or the person who asked this question just give me a call or drop me a message. Then we can talk about this. But yes, from a practical point of view or from a software point of view, it's the same thing. If I count sugar beets, if I count ears, or if I count trees, if I detect diseases, or if I distinguish varieties, it's basically the same problem, but another target in the end.
Understood. Thank you. Yeah. So one additional question that popped up. When customer is interested in using your imaging processing capabilities, but they don't have their own drone, can you maybe organize the flights with the right hardware?
Yes. So what we are doing is we are partnering with different companies, and we can basically organize flights worldwide. Is a bit too a bold statement, but in the in regions like America, also in North Africa and South Africa, Australia, Central Europe, or Europe in general, we can organize flights, yes. And we can also guarantee that the flights are then done within a certain quality. So they are under a certain quality assurance process, so that you can be sure that the flights which will be organized by us will have the or will fulfill the requirements we need to serve a good quality analytic.
Thank you a lot, Philip. One more question for you, I would say. Can we use your technology to perform phenotyping also on less occurring crops, such as medicinal plants or spice crops?
Yeah, thanks for the question. Yes, generally we can do this. So as for the example for the trees, there is no limitation in the end on what type of crop we are addressing with our analytical pipelines. Of course, if you have the typical crops such as sugar beet, cereals in general, corn, soybeans, so the prominent cash crops, of course, there is much more data already available. So it's helping definitely to transfer this into large scale applications without supervision, but also for less occurring crops. We are good at basically on a few samples getting a classifier running. For just to bring an example, we exploit sugar beet data in order to get a better prediction for soybean, for instance, or for other crops. So we are able to transfer the training data to different domains, and therefore we can easily also adapt with less data to new problems. Yeah.
Thank you a lot, Philip. I see also that the time is running up, so maybe let's ask the final question, and then for the rest of the questions, we will come up via email answers. So is the technology also applicable for other applications without drones, let's say in, for example, greenhouses?
Yes, for sure. So PhenoInspect's core competence is basically the vision analytics part. Basically, if the camera is carried by a drone, or it's a smartphone, or it's a robot which carries a camera through the greenhouse, or it's a stationary camera, the technology which brings the interesting data out of the image data is still working for different environments or different applications. Yes, there's of course the question how feasible is bringing a camera here and there, but greenhouses is, I think, a good example where it's a good application for applying this kind of technology. Yes.
Thank you a lot for both of you, also for the presentations and for the questions that you have answered. Also for all attendees, we will come back to the questions that we didn't manage to answer during our session. And also just to make a note that the session was recorded and everybody should be able to get the recording of the session. Thank you once again for your time, and thanks once again for the presentation.
Yeah, thanks, Dejan, for helping with the questions, and thanks again to Philip for all your insights and your answers. Very much appreciate. So yeah, we are running out of time, but it was, I think, very valuable. So I will now close the webinar. Thanks again for all viewers joining this webinar series. Looking forward to see you again at the next webinar. Like Dejan already mentioned, this webinar is recorded and we will provide it within the next 2 or 3 days on our website. So you can go back and view it again if you want, or also can reference to someone who also would like to see that. Yeah, thanks again for all joining, and also again to Philipp. Very, very interesting topic. And yeah, thanks for the viewers, and have yourself all a wonderful and great day. Thanks a lot.
Thank you. Bye all.
Bye-bye.